All right, there we go. Yeah, we'll go ahead and start it. Just see if he hops on. Sure. There we go. Okay, so have you gotten a chance to read Progress Report 3 or look at the technical report at all?
Um, I have not read the technical report.
Okay.
For whatever reason, they do not make the technical reports available to the safety reviewers.
Hmm.
So
Okay, that's a little
I
odd.
don't know why that is, but we can talk to Ben about it because that's his job.
Oh,
So
okay, yeah, we can complain to him. Well, in that case, then this presentation should give you a pretty good overview of where we are. So, February 2024. So you recognize people's faces. I'm team captain. We have Fred, who's joining us virtually. He is a payload captain. Pete, which is behind me here, he's aerostructures. Gerald is virtual. He's a recovery. Leo behind me is propulsion, and then Shannon to my right, which I can show you here. He is our one of our social media leads, also a current member of aerostructures, and should be taking over for them next year. Uh, and then Natalie
all right,
is
who
the
will
same.
be taking over next year?
Oh, Shannon. Right here. So we've got aerostructures first and second in command with us. Natalie will be taking payload. She has the current 4U Sauron with her right now. She could not join us tonight, um, but she's also Fred can talk to you guys about payload stuff if you have any questions. Um, okay, so this year's rocket, I know you mentioned 25 feet, kind of long. We're down to 22 and a half, and also down to 137 pounds. Our new apogee predicted right now is 11,600 feet. We have a static fire for a smaller sustainer motor happening tomorrow, actually. So once we verify that, that number will be updated a bit. And then once we get final weights, everything put together. Payloads, we have two. Let me move this box real quick. There we go. We have two payloads. One deployed from the sustainer, that's Sauron 0.0, and then one deployed from our booster, that's a quadruped, and you'll see what those look like here in a second. In terms of separation points, we have five. Two, of course, at the interstage. One is a shear pin separation for the main of the booster, and then one is separation for the sustainer interstage coupler. Then we have our nose cone is the same as the booster with the main packs forward or behind the payload. And then we have two drogues on the booster side for each sustainer and booster. And again, I'll run through that in more detail here in a second.
Okay, a quick
Yeah.
question, maybe back up to the, okay, so is there, there's an altimeter bay in the middle, but there's not a separation point there?
Correct. So our altimeter bays, they're both hard point. We have the black powder charges on either end here, and then they're blowing the far bulk plate off. So we have shear pins and shear. Can you see my mouse?
Yes.
Okay, yeah. So we have shear pins here and shear pins here, which are sheared by electronics from this bay.
Okay, but there are two breaks there. It's just not a separation point.
Correct, correct. Yeah. And here in a few slides, I actually have all of the hard points and shear pins and everything mapped out. We'll go through those. All right, so just one more quick overview. Our total length, that's an old number, it's 22, but we have 3.4 stability on the full stack and 1.5 on sustainer only. We can increase the sustainer. We have a little ballast up here, and that is a little on the edge of the comp requirements. We're actually tending towards 1.6, but we're keeping an eye on that closely and adding ballast as needed.
How did you lose so much weight? I mean, the last number I saw was 164, so you dropped
Yeah.
30 pounds.
So one thing we did to estimate our weights in the past, we've underestimated the rocket weight by 10, 15 pounds. So this year we ended up weighing all of our components individually and adding an additional weight for epoxy. We assembled a subscale or the full scale sustainer for our test launch, and our weight was some 15 pounds lighter. And we realized the reason for that was a mixture of changing or having high weights for our electronics, and then also overestimating our epoxy weights. So this new weight is actually based on the assembled sustainer weight, and we've adjusted the booster and sustainer accordingly. So the booster was about 10 pounds heavier than the sustainer with the previous weight. And what we did, sustainer is 47 pounds, booster is now 57. Okay, so ConOps, I think you're pretty familiar with it at this point. We have two-stage, sustainer comes off the booster. Booster hits apogee, you have the drogue deploy, and then quadruped comes out with the main. And then our sustainer is the same thing, except higher apogee, and then point with main. And I go in more detail here in a second. Yeah, so the open rocket, like I mentioned, we're at about 11,000 feet, and then 4,500 for the booster apogee. Come down here. Testing, we've done sustainer test flight, full the subscale for just sustainer, and then subscale for both dual stage and sustainer. I guess it's both progress reports. We have a sustainer static fire complete, but we are going to be redoing the static fire tomorrow, like I mentioned, for the smaller motor. We have our booster static fires complete. It's looking good. And then, progress report 3, technical report. One thing worth noting is our sustainer subscale flight, or dual stage subscale flight, we were able to validate the staging and ignition with the Blue Raven. We were also able to test our new altimeter sleds, which you see here in the middle, and they've been scaled up, of course, for the full scale. And then we were able to make sure the payload's deployed as expected and properly without getting tangled in the rest of the recovery hardware. One thing worth noting too with the sustainer is we were able to validate a lot of the building practices, and you'll see that the ConOps for the sustainer is identical to those of the full scale.
Okay. Yeah, on each slide, give me a little pause to ask questions because
Yeah, of course.
as we go along. You had listed a full, kind of an all-up flight of the rocket on April 27. That was in your third progress report.
Yes. So we were actually gearing up and ready to go out to North Carolina for that flight, and we got a call or an email 2 days before telling us that they had closed the field early because the farmers wanted to plant their crops early. So we had to cancel our hotel, put the bullet on a lot of travel plans. And we have our next window would be later this May, and that's after everyone graduates.
Okay. I noticed on your subscale flight that the sustainer took a long time to come up to light. Why did that happen?
Yeah, so we had our delay on the ignition at 3 seconds, which from that flight turned out to be a little too long. That's close to the delay we had last year for the full competition motor, but we realized that with how the COTS motor performed, it was a bit too long. But that was yeah, a delay issue. And one other thing that we were able to confirm. So this time around, we're doing a 2 second delay.
Yeah, just one thing that I'm kind of passing on to the teams, just to,
Mhm.
I'm not supposed to help all that much, but since Ben's not here, one thing that is just really important for getting the stages, the sustainer lit,
Mhm.
is to hold in the igniter
Fold in.
in some manner so that it stays in the rocket even after it fires.
Right.
And so if you think about that, are you planning to use an igniter stick?
Yeah, so what we actually ended up doing was we put the igniter on a stick and then put it up into the bottom of the sustainer motor and then tape the stick in place like up against it. So it was pushed up against the forward closure.
I'm sorry, pushed up,
The igniter on the stick was
right?
pushed up to the back end of the motor.
Okay.
Yeah, so we did have a stick.
Okay, yeah, the trick to getting sustainers to light is to do something that holds the stick in a manner that doesn't prevent the igniter gases from being ejected. So for example, if you held in the stick with the little orange cap that goes over the nozzle,
Mhm.
that's how you don't want to do it,
Okay.
because the cap just gets blown out along with the stick. And so you don't really, it's sort of like you want to have the cap on there so that you don't pressurize the core from a separation charge and so forth. But there needs to be some way of holding in the stick that's separate from the cap. So that, if you took the cap off, for example, you might have something holding the stick in, but most of the room in the nozzle is still open, so the gas
Right.
can come out. And all you have to do is just hold that stick in for a couple of milliseconds and after it fires, and you'll light the sustainer.
So maybe instead of covering the base here with tape, we could do that, but put like holes in it or something, like small vent holes.
Well, I've done it different ways. I mean,
Okay.
I've done it with tape like that, but I mean, and I can't remember. We did it for some team last year, and I can't remember who it was. But it's almost like you put a piece of tape over the end of the stick and around the nozzle, so that holds the stick in.
Mhm.
And then if you want to cover the whole nozzle with tape, if you want that to, then you actually take a little piece of paper towel and put it over the piece of tape that's holding the stick in, and
Okay.
then you cover the whole back with tape. And that way, if that tape gets blown off, it doesn't take the stick with it.
I like that. Okay, that's a good idea.
Yeah, and there's a whole bunch of ways to do it. I actually use a couple little pieces of string, and I'll tie them around the stick and super glue it so that holds the stick in.
Okay.
There's a lot of ways to do it, but the
Yeah.
secret is to hold the stick in so it can't get blown out, but to
Okay.
leave a gas path so that it's clear. And
Gotcha. Do you think that could have also caused the delay in ignition?
well, that's sort of why I was asking the question. The kind of the follow-up question was how long was there between the time the igniter fired to the time that the motor came up to pressure? And if that was more than say a second and a half or 2 seconds, then you start wondering, maybe the motor didn't get fully lit, or it got lit maybe not all the way at the top, or something, if the stick was being ejected. So
Sure.
that's why I asked the question, because that is one symptom, or one of the things that can happen if the stick is not fully held in.
Okay. Yeah, we will. We should rewatch that and time it, make sure that's um not the case. And also, I like that. Thank you for the advice. Well, okay. It looks like we have a lane.
The other trick, and I think I noticed you said you were going to do an all-up test.
Yes. Yeah. So we'll do an all-up test before we come out to Spaceport, and then while we're out there at the pad as well.
Yeah, now one trick that can make the all-up test easier, and if you're using a stick,
Uh-huh.
and what I like to do is I'll have the wires coming down to the igniter and then go immediately up into the motor. So no slack. I don't have a bunch of extra wire there.
Okay.
And the thing that makes that work is if you just tape the igniter wires to the stick halfway down from the igniter, you'll find that you can pull the igniter out. Okay, if you tape the wires all the way down the stick, now you can't take the igniter out because
Right.
you
Right.
don't have any slack. But if you only tape it halfway down, or a little short of halfway down, you can pull the stick out. It's a
Okay.
sort of an optical illusion, but you can try it, and it will work. And that allows you to do the all-up test without having to have a whole lot of extra wire down.
That's a good idea. Okay. Yeah, because we usually we do only tape it halfway up the stick, but we have a lot of slack as well with our wire.
Yeah, I mean, you can do it. I mean, I like to not have all that wire down there because if you're gonna have a separation charge, you can damage the wires that are down there.
Right.
And so, I try to minimize the amount of wire and then also protect that wire, so that it's not getting damaged. And, you have the conflict because you want to take the igniter out.
Yeah.
But for the all up test, but if you just take it halfway down, you can pull the stick out.
Okay. Yeah, we'll do that. And we'll make sure our wires are short for the interstage. All right. Are we good to keep going?
Yeah, yes.
Yeah. Okay. Cool. All right. So yeah, like I mentioned, we were able to test the general design for the rocket, the configuration of our altimeters, our payload deployment, and as well as the interstage coupler. Blue Raven worked very well for this. We are using it as the secondary for our eBays, and we used it for ignition and separation of the sustainer.
And you have a separate altimeter bay for the Blue Raven that lights the motor?
Yep. So our three altimeter bays, we have the recovery for sustainer, Blue Raven altimeter for ignition and air start, or separation and air start, and then the booster recovery.
I'm sorry, you said the third one was the separation ignite?
This one is separation and air start, the middle one.
Okay, and what was the next one?
Last one is booster.
No, there
Just
was one
recovery.
there in yellow that you said something about.
Oh, the yellow ones are our payloads.
Okay, all right,
Yeah, if I did, I may have just been at the wrong place with the mouse.
okay.
Yep. All right, so general construction now. Like I mentioned, here's the specific ConOps for the sustainer. We hit apogee at 11,600 feet. Under drogue, we're coming down at 99 feet per second. We hit main at 1,500 feet. That puts us at 28 for the rocket and 25 for Sauron, the deployed payload. Here's the
Okay,
top.
back up a second. So this is the sustainer and you've got 28 feet per second on the sustainer. What is it if the motor doesn't light?
If the motor doesn't light, that's actually a very good question. I think we go up to
Yes, it is.
31 or 32. But let me check that. Let me confirm that for you. I think it's 32.
Okay,
Okay. Yeah, I will send that over to you after this. So,
yeah, any time on a two-stage, they're gonna light half the time typically, so you have to have a safe recovery in the event the motor doesn't light.
very good question. Okay. Yes, I will send that to you right after this. Okay, so our sustainer here on the top, we have pier pins right on the nose cone. Those are 4 632s. Moving down, we have our payload packed forward of the main and chute protector, or the chute bag. That's a chute bag there. For this, I know one of the things is what pulls the chute out of the chute bag. We have the short end, which I'll show you in one of the next slides, of our shock cord is actually connected to the nose cone. And so that's pulling when the next nose cone gets ejected. We are pulling both the payload out as well as the main chute from the chute protector. So the momentum of the nose cone is acting kind of like our main drogue or guide chute. Next, we have two hardpoint connections. These are our avionics bay. This is the ABS printed bays that we used for the subscale flight and that we are using for the full scale. Behind that, we have our drogue, which is just right here. Kevlar 3-foot, 40-foot, half-inch shock cord. Okay, it looks like we have both Ben and Elaine now. And then we have another 4. One second. There we go. Another 4 shear pins for the forward end of the coupler. Then our pressure electronics and the staging electronics. which are using the same sleds. I have the same picture here, but it's the same sled that's being used for those electronics. And then a hard connection on the aft end, and then our pressure transducer, and then the pressure thermistor and strain gauges, which I'll talk about here in a bit, on the motor tube. And I mentioned strain gauges. That is actually something we're going to be doing next year, not this year with the rocket.
Okay,
Yeah.
on the sustainer, you said 4 number 6 shear pins?
4 632s. So a step up from the 440s.
Okay, and how much weight is up there in the nose cone?
Good question. So it's right here. We have, I think it's 3 pounds of ballast.
3 pounds.
Yep.
Okay.
Yeah. Good question.
Yeah, if you've got 3 pounds, then you need some shear pins there.
Yeah.
And you said that is going to pull out both the payload and the main. And,
Yes.
Okay, so does that mean you're not using a deployment bay?
So the main does have a deployment bag that's connected to the coupler here on the back end. So what happens is at apogee, this section of the rocket, the payload bay is actually pointing down, so the nose cone is pointing towards the ground, and we have black powder charges go off here at this joint. We shear at the nose cone. The nose cone gets ejected downwards. The payload falls out and is pulled out by the nose cone pulling on the main chute. So the nose cone shock cord is the short end of our 3-loop, and it's what pulls the main out of its chute bag, or the deployment bag.
Okay, so when your payload comes out, basically you just have to dodge the nose cone.
Right. What's luckily with the testing that we did, both with the subscale and the launches last year, the payload does miss the nose cone. Its chute deploys relatively quickly, and it gets out before the main chute deploys on the rocket, so the two don't get tangled.
Okay, so when so you have a deployment bag in there basically to just protect from the charges.
Exactly. Yep. And as you'll see when we walk you through the rocket, we also have chute protector tied in line with the main shock cord for the payload to keep the payload chute protected as well.
Oh, okay. Okay. Yeah. Okay.
Yeah. It'll be easier once we show you.
Okay. So the shock cord then is going to be attached to the bottom of the shroud lines.
Yes, and actually I can show you here on the next slide. This is
Okay.
how that's set up. So
Well,
this is the sustainer.
let's come back to that then. Go back and talk me through the booster brakes.
Oh, actually, so I have it set up. We have sustainer, and then we'll talk through the booster.
Okay.
Yep.
That works.
Yep. So sustainer and booster have nearly identical recovery schemes, except for the sustainer we have the nose cone, for the booster it's the inner stage. As I mentioned, we have 40-foot 3-loop half-inch tubular Kevlar for the drogue section. This is rated for 7,200 pounds, good for what we're doing. Main is 3/4-inch Kevlar. I don't have it there. I think it's rated for 9,600 pounds or something. Stainless steel swivel links, those are rated for 3,000, and then of course our quick links are going to be the limiting factor at 880. We are standardizing those, so we're going to be buying new quick links for everything. And then our 3/8 U-bolts on both the couplers are for 1,000 pounds. These are what we've used for competition in the past as well. So
you're upgrading the 1/4-inch quick links.
yes, yeah. So we have 1/4-inch quick links this time around instead of the smaller ones.
Okay, I thought 1/4-inch had a little higher rating than that. You might check into
I will. I got
sourcing the quick links because that seems on the low side. That's always the area to kind of watch out for. Is the quick links. Those are the those can be the weak link, so to speak.
Okay. Yeah, we'll see if we can find higher strength ones of that way. We may be looking at some some not great ones.
One thing I noticed when I went, and you can show me the physical equipment here. One thing I noticed just going through the open rocket file is that you have a lot of hardware, a lot of links, a lot of swivels. Jim's rule of rocketry number 17 is minimize the hardware to the extent you can, because that just can be places for harnesses to tangle.
Okay.
I was doing a review for a team, and they were doing a Y connection, and they had 3 quick links instead of 1. You know, why do you have 3 quick links to do a Y connection? And as well as just hardware is cool. And well, not necessarily.
Sure.
I look at things like swivels and so forth on main parachutes. Is that really necessary, given that it's not going to be in the air very long? I would just recommend going through and, if there's hardware you don't really need, you might take a look at it and see if you want to use it.
Okay. And actually, on that note, one thing I can show you, we could, if we wanted to, take our swivel links and just loop them through the shot cord, cinch them down inside, like creating a third loop. And so that way we get rid of at least one of the quick links and the quick swivel quick configuration. That's one option. Yeah.
Are you recording this?
Yeah, we're recording.
Okay.
Yep. I just confirmed to be sure.
Yeah, I mean, if the swivel's already integral to the chute, I wouldn't worry about it.
Okay.
But, it's just, I've had a couple L3s that I've done where people just overloaded on the hardware, and sure enough, the recovery system tangled. So, just be judicious in what you're using.
Okay. Appreciate it. Yeah, we'll go through and make sure everything is simple as possible. Also with the bunching of our shot cord and everything, we try to make sure they don't get tangled. Okay, so for the booster, again, very similar deployment scheme. Apogee, instead of 11,000 feet, we're at about 4,500. We come down with the booster a little fast at 111 FPS on the drogue, and then 29 FPS under main, 27 for the payload. This booster section. So one thing is, if the sustainer doesn't ignite, or even if the inner stage doesn't separate, because we have the friction fit and we have the each independent recovery system, right? Should they not deploy, you'll have 2 chutes compensating, and the difference in height between them is such that it can be staggered. Okay, so 27 for the quadruped, and then same thing figure here. So we have shear pins here at the interstage coupler instead of the nose cone. Again, these are the 4 632s. We have our payload. This is the quadruped, deployed quadruped, packed in the same way as the 4U Sauron. This is deployed with the main at 1,500 feet. We have our avionics bay, same configuration as those for the sustainer. And actually, as we'll see, same programming too. Our drogue, 3 foot, 40 foot Kevlar, shear pins, same, the 4 632s, and then our hard connection. We do have room for an av bay here, but it looks like we will not have any electronics going in. So we'll be removing the avionics bay in that area, the sled there. And then we have our 115 millimeter motor for the booster. So that's no motor tube, just a direct mount. Okay.
Okay.
There we go. All right. So like I mentioned, the recovery configuration for both is very similar. The only exception here is our interstage coupler serves the role of the nose cone in pulling out the main and the payload. And then also our main is a 10-foot main chute for the booster, because it is heavier, instead of the 9-foot, which was for the sustainer. All right, and quick overview of our recovery subsystems. So this is just altimeters and the avionics space. So like I mentioned, we've changed the design from polycarb, which we saw last year, to the 3D printed sleds. These have worked very well for the subscale and all of the preparation for the full scale. They were also functioning very well. Altimeter programming. So the booster, we have drogue at apogee, and that's going to be with our Altus Metrum, the Easy Mini as our primary, and a main at 1500 feet. For the Blue Raven, same except apogee plus 1 second, and main, this should be corrected, is 1400 feet. For the sustainer, it's the same. Again, main should be 1400 feet here, but we have drogue at apogee, featherweight apogee plus 1 second. So what's really good about this configuration is even though we have the two sections are experiencing different apogee and separation, when we're programming the altimeters, we don't run the risk of mixing up which is which, because they are the same. So once we hit apogee, and then once we hit the 1500, everything is identical. And then for the staging, so stage separation is just timed on burnout. I know last year we talked about timings from launch. That's something that we could do again this year, although the motors are performing pretty reliably. This static fire tomorrow will kind of help us make that more concrete. But our burnout plus 1 second also allows us to account for any tails on the curve, making sure that we don't detect burnout prematurely. Air start happens with burnout plus 2 seconds. Like I mentioned from the subscale, the 3 seconds was a little long. But the two big things for this one are altitude lock. So the altitude has to be at least 2100 feet when burnout occurs. Doesn't work if it's after burnout. It has to be when the burnout occurs, or when the burnout plus 2 seconds occurs. And this is actually 70% of our old 3,000 foot estimate. So that's actually gonna be 2,800 feet, 70% of the 4,000. And then tilt lockout is 20 degrees. If we exceed 20 degrees at any point during the flight, the air start does not trigger.
Okay, and I sent out a little one pager on the staging program. Did you receive that?
When did you send that out?
I don't recall the exact date, but I sent it to all the two stage teams at the same time.
I don't remember, but I'll check and see if we received it. I don't remember seeing it.
Okay, well, yeah, do make a note. If you didn't get it,
Yep.
then let me know and I will resend it. It's not going to be a whole lot different from what you have.
Okay.
That one of the things it will with the Blue Raven, one of the things that you can do now that you couldn't do with the Raven in the past was to specify a time greater than and also a time less than.
Oh.
Okay. So you would determine the altitude at where you want the igniter to fire, and then that becomes the time associated with that becomes the time less than. So that might be 2.1 seconds. And then you have to set a time greater than, which might be like 1.9 seconds.
Right, right.
So that you've only got a narrow window in there when you can actually light the sustainer.
Okay, that's a good idea.
And so that's listed in that one pager that I sent you. And so I'd like you to do it that way, unless you look at it and you say, well, we want to do it differently than that. And then you can come debate me on the topic and we'll resolve the way that we end up wanting to do it. But I sent that out to the teams, and because most of the teams are using either a Telemega or a Blue Raven.
Okay.
And employ that strategy now identically in the two devices.
Yeah, I'll look for that document. Make sure we received it. And for the window, would you say like half a second would be the ideal?
Well, it literally doesn't need to be more than a tenth of a second or so.
Okay.
I would typically make it 2/10 of a second just because I don't want some kind of rounding to get the time too short would worry me. But the altitude check, which is the 70% of the value that you expect, is associated with the time less than value.
Right.
So you can use a time greater than value that's a little bit less than that. And if you make your altitude, that's probably where it'll light is on that, in my example, the 1.9. If you were straight up and had a good flight, you'd probably light at that point. But then you can't light more than the 2.1 seconds. You close the window. And
Okay.
that concept of closing the window is critical because you don't want to, Cato on the pad and have a slow rise up and you just barely make it to the altitude check and then you fire the sustainer because you didn't close the window. So you got to have that at both times in there.
Sure. Okay, we can do that.
Okay.
That's good to know. When did they release that update?
Well, I'm not sure it was released. I sent it out as an email on,
Okay,
yeah, in the same way that I send you review comments.
I gotcha. Okay, yeah, I'll look for that. Make sure we have it. Okay, yeah, here's a close up for the sleds. This is for the subscale, but this is the same layout that we have for the full scale rockets as well.
Okay.
The one difference between the full scale and the subscale is, as I'll show you here, we have screw terminals on the bulk plates for the full scale rocket.
Okay. And
And
are you using any lipos? I see one there.
yep, so we have one lipo that's for the featherweight. It's what they sell it with, and it's been tested.
Okay.
Yep. All right. So wiring, Easy Mini is going to be the terminals are wired through ground for the E matches, and then we have a screw switch for powering the Easy Mini altimeter. Blue Raven, their terminals start off hot, so for the backup Blue Raven on the altimeter sled, we have a screw switch connecting to both the altimeter itself and the E matches. And then for the staging and air start, we have additional screw switches between the air start and separation charges, so we can arm each individually.
Okay. Um, and are you hooking up the Raven in the recommended way, which is to, I'm not sure how to describe it. But I think you're doing it. Yeah, you're switching the positive instead of the ground.
Yeah.
Yeah, and watch out on the Raven because the posts are part of the circuit for the Raven. And I don't think you have a problem with that, but just be aware they're part of the circuit.
Okay, so if we had any shorting between the E matches to those.
Well, or to the sled or to the airframe or something where you could, have a pathway that went through the standoffs down to something.
Right. Okay, yeah, we'll watch that, especially because on the back end we do have, the batteries and stuff to make sure there are no floating wires.
Yeah, that has gotten people before, that those electrically included standoffs on the Raven. So it's just a caution to watch out for.
Okay.
I don't know why he does it that way, because it's sort of dangerous in certain situations. Okay.
All right. Okay, and then just quick propulsion as it applies to rocket ConOps. So, as I mentioned, we have the thermal analysis that we're going to be performing on the rocket motor, and this means putting in external sensors through these holes through the body tube and the inner motor tube. We'll show you where those are and how that's going to line up on the physical rocket, but that's something that we have not drilled yet because we wanted to get your official word on drilling these holes beforehand. The way it's set up is,
These are just drilling holes in the body tube to install the sensors?
yep. So these we're drilling holes in the body tube and in the motor tube here, and then they're being pushed up against the motor casing, the metal motor casing.
Okay, I don't have a problem with that.
Okay, cool. All right, as I mentioned, so they're here on this part of the sustainer, and we're just getting temperature data from the casing on different parts of the case during the flight. And then we'll also have a in-flight pressure transducer, which is going to be connected to our second stage electronics coupler. And then payload, again, as it applies to the rocket, we have Sauron, which is the 4U CubeSat. It's not depicted here, but our recovery plate has a 1/4-inch U-bolt that's used for recovery. I remember last year we were using an I-bolt and ended up switching to a U-bolt. So this year we're on that. 10 pounds, it's descending at 27 feet per second. And then Sara, it's a quadruped. We'll show you the updated design here in person. The recovery system is going to be attached directly to the quadruped, and this one's coming down at 28 feet per second. It's a 12-pound payload. And that's all I have there. We have the video of our subscale dual stage flight if you want to see it, or we can go ahead and just dive straight into the physical rocket.
Yeah, I just watched the video of it a little bit ago. If there's anything you want to point out on it, you know, we
Nothing
can,
worth
but
noting
the
except
only
that
thing
the
I
time.
noticed was the time seemed to be a long time, so I would just check the, you know, how long was it really from igniter to coming up to pressure.
Right. Yeah, and I was going to say that'd be the only thing really worth note with that. All right, so we'll go ahead and transfer over. I'm going to stop sharing my screen here. And, we're going to transfer over my phone, run you through rocket there. Okay. So I'm going to.
Let me ask you before we do that.
Sure.
On the shear pins, have you done all the ground testing with those shear pin combinations?
Yeah, so we did ground testing for the sustainer section, and we have ground testing for the booster section, and then the newly built sustainer coming next week.
Okay, just
Yep.
one comment. And you know, I haven't poured over the you know, the specifics of the rocket, but I typically, you know, worry a lot about the shear pins up at the nose cone end so that you don't put out a main and that sort of thing.
Mhm.
I was wondering about the shear pins on the interstage coupler though. That may not weigh all that much. And do you want to have shear pins that are that heavy at that location?
It's a good question. So the reason we have shear pins that size, one of the issues we've had in the past, didn't happen last year because of the Cato, but the year before it happened. The payloads in the payload bay, they will, once the drogue deploys, they'll swing down, and we pipe them really tight so they don't shift a lot, but there's still some compression that happens, and we'll get a main deployment at apogee if our shear pins are undersized because the payloads will shear the pins early. So we have to have the larger shear pins to make sure that doesn't happen.
Okay, that's a good point at the booster.
Yeah.
Okay. The other thing that I would typically do is maybe ease off on the shear pins at the drogue section. You know, that's usually not a section that's going to tend to, you know, separate. I mean, you know, you're sort of worried about, you know, keeping the rocket aligned. Maybe that's one reason for using shear pins. And also just to prevent drag separation if we thought that was going to be an issue. But on a rocket like that, I might have a couple of number 2 shear pins.
Okay.
You know, there's not really a big reason to even shear pin that location. And you know, and I'm not saying it's not okay to use the heavier shear pins, It's just not really necessary.
Okay.
In a conventional design. Now you have to think about whether or not that is your design.
Well, I mean, it's good for us. We can size them at least smaller because we don't want to damage the recovery hardware more than we risk it as it
Yeah,
is.
I mean,
Yeah.
you can back down on the charge size that you're using. You're not gonna maybe as likely damage the airframe.
Right.
So, you can look at it and say, is there a reason that we need to have? I mean, is there any chance that we're gonna shear pin or that we're gonna drag separate these sections and that we would want? Normally there isn't. And so all you're really trying to do is to align those sections, keep them from moving when you're on the pad. There's not really a big flight reason to have them. So just to offer that comment.
Okay.
You're not really trying to, you want that section to separate. And
It's a good point. Yeah. 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 Okay. We'll make sure the drogues we'll probably size those or decrease the size on those a bit. Maybe go down to 440s and just three of them. We do like to keep them together just because of like shocking between booster burnout, and we would avoid possibly separating too early. I guess just team precedent would be stick with shear pins. So we have some retention, but yeah,
okay,
yeah, okay. Then if we're good here, I can go ahead and move you to my phone, and we'll start looking through that. That's going to be here. Move to stage. Yeah, can you see?
let me try to get that window up.
Yeah, I'm gonna mute these.
I'm not sure. I know
Okay. How's that?
Well, I can see it. It's just one of 9 small windows. I'm trying to figure out how to make it the main window.
Ah. Uh,
If you right click on the window that you want to make bigger, you can pull up the option that says move to stage and it'll pin it.
Okay, so now I have 2 windows. One is the camera and one is your window, Shannon. Oh, now I have to figure out how to.
Um,
Oh, I can just move it. Okay, I'm set.
all right. Sounds good. Okay, so would you like to start from the front of the rocket or the back of the rocket?
We can go from the bottom up.
Okay.
If you can figure out how to do it, with the camera, the audio is kind of really fluctuating a lot. So maybe you can hold it or talk to it sort of consistently so you don't fade in and out.
Okay, how is this right here?
That sounds fine.
Okay. So, as I mentioned, we have a non-motor tube retention system for the 115 millimeter motor. That slides in to this centering ring and fin scaffolding, and then we have our retaining ring that goes over like this and holds the motor in place.
Okay, it doesn't look to me like that thrust ring is pushing on the bottom of the airframe.
Yes, so this thrust ring, we have a lip. Oh, sorry, we have a lip that goes. So the motor casing has a snap ring on the outside. That rests on this thrust ring. Then this is pushing on the fin tabs, which are pushing on the other thrust rings or the other centering rings, and then through the fin tabs also it's transferred to the airframe.
Okay.
So our thrust goes through this ring here. It's actually 2 centering rings, then through our 3 fin tabs to the rest of the airframe.
Okay, it looks to me that it's okay, just as a matter of general design. If you can figure out how to make that push on the airframe, you'll get less cockeyed looks from judges.
Okay. So you mean you want the motor to push directly like on the airframe?
Well, I mean, I would generally, you try to get a thrust ring, whatever it is,
Uh-huh.
to push on the airframe itself. Now, I don't know if you're pushing directly on those centering rings. I'm not sure exactly what you would have done. If you're pushing on the aluminum, then you might have made the diameter of the aluminum a little bit larger and covered the bottom of the airframe
Right.
instead of the centering rings. So
Well,
just as a general practice, that would kind of be what you want to do. Now you have the ribs in there and they look like they've got lots of epoxy, so I think you're okay.
okay. Yeah, what we could do, I mean, we could take our aluminum, make the outer edge wider, right? Go over this lip, and the aluminum is hard pointed to the centering ring. We have bolts that tie this to place. So it would be going through those bolts and into the airframe, which is somewhat indirect, but still.
Yeah,
Yeah.
I said, I mean, I think you've got enough structure in there. If you were just pushing on a centering ring higher up in the airframe, I'd wonder about that. But
I gotcha.
you've got enough structure in there as it is.
Okay. Can you get your phone
And
outside?
how thick are the fins?
Fin. So these are the 3/16.
Okay.
Yeah. We made them bigger on both the sustainer and the booster. Yep. All right. And then if you want, we can move our way up. So coming here, we have our first hard point. Like I mentioned, it's just coupler to body tube. And we have four 632 bolts that go through on either side. And then you can see the same holes over here to secure this in place.
Okay, so you're going to have how are you going to attach that hardware?
Yeah, so we have
I mean, you're going to
these.
have to reach inside that coupler tube, right, in order to.
Yeah, so you kind of see here, we have nuts on the other end.
Yeah.
They're flanged nuts epoxied in place. And so we just screw our bolts directly in from the outside.
Okay, and there are four of those?
There are four. Yep, two on this side, and then two on this side. Yeah, here's an example of one right here.
Okay.
And the placement of those is to accommodate the shape of our sleds, our new altimeter sleds, because we have on the switch band 3 holes. This doesn't have an avionics bay, but I can show you this one here. Oh, this one doesn't have the holes drilled yet. We have the 3 holes on the edges that line up with our 3 screw switches. So it's just make sure they don't interfere with one another.
Okay, and what would go in there? Is that where you're not using the?
This is the one we're not using.
Yeah, okay.
Yep. Yeah. Okay, so we have a hard point on this end. This end is shear pinned. And this is the separation point for our drogue. So like I mentioned with the drogue, it's 1/2 inch, 40-foot tubular Kevlar. It's a 3-foot drogue on that. We have right now, it's a quick link, swivel link, quick link. Like I mentioned, we're changing our quick links to all be 1/4 inch with these. But they're hard pointed here, shear pin here, and then we come to our second hard point for that shock cord, which is on the recovery coupler for the booster.
Okay, back up a second to the
Yeah.
recovery, to the drogue section. So that looks like a Kevlar drogue.
Yes, sir.
Okay, and how large is that?
3 feet.
3 feet, okay.
Yep.
And so that's the one bad hawk 1/2 inch
Uh,
tubular.
yes, this is actually the Wildman 1/2 inch. I think he gets it from one Bad Hawk. I'm not too sure on that.
Well, I'm pretty sure it is from
Yeah.
the masking tape. That's a one bad hawk.
Okay.
And that swivel is it goes to the drogue.
Right. Yep.
Okay. Okay,
Okay. So then we come up here. This is the so this is just the drogue bay where we pack the drogue in. This is our coupler for drogue and main. Coupler here, we have a hard point for the drogue, and then these are more of the screws. So these are bolted in. Same here, bolted in. No shear pins on this coupler. This coupler has our first avionics bay, which we have one pulled out up here at the end, which I'll show you. And this is the staging. So Blue Raven secondary, Easy Mini primary.
okay, so one thing I missed, maybe,
Yeah.
maybe down lower, you probably have a U-bolt.
Yep. So here we have
Yeah, okay.
U-bolt.
Yeah, is that the one you're planning to use?
Yeah. So this is the 1/4 inch.
Okay. And remind me what the rating on that was, if you recall.
The 1/4 inch U-bolt, I think, was 1,600 pounds or 1,800 pounds.
Okay, all right.
Yeah.
And so you've got a piece of all thread that's probably holding the bay together.
Oh yeah, yeah. So this is the
Center.
3/8 inch.
Okay.
And that goes through the coupler to the other side here. We have a lock nut on one side and a regular nut on the other.
Okay, so that becomes structural in your design.
Yes.
Okay, and what's on the other side of that bulkhead?
The other side of this.
Yeah.
So we have another nut that goes in on the other side. We can't tighten it as well on both ends, but on one end we have the lock nut and then tighten nut on this end to keep that stable. And then this end is just one nut, but then the nut here.
Okay. I guess just looking at that, you know, that bulkhead is part of the structure.
Mm-hmm.
And you've got 3 holes poked in that bulkhead, right close together.
Yes.
And I'm wondering if that weakens that area such that, you know, you could have a failure if you had, you know.
Yeah. No,
Part.
that's a really good point. We have other bulk plates. We'll probably replace this. We actually will replace this one.
Well, I'm not concerned about the extra hole that's drilled. I'm concerned about the 3 in a row.
Oh.
And
Oh, I see. Like these, this.
yes, because normally you'd like to have a U-bolt on there, and you know, some sort of a metal backing on the other side of it.
Okay.
I mean, one thing you might consider is just to have the U-bolt maybe off center from the from the all thread down the middle.
Oh yeah, like put it maybe up here.
Yeah, sometimes on 6-inch rockets, people will use 2 U-bolts, and they'll just put a Y connection on there, and
Okay.
you know, just you just have to be careful as the rocket gets up. You know, if you were a 4-inch, you might be less concerned about it, but as you get up to, you know, a 6-inch and larger, you know, if your bulk plates are part of the structure of the rocket, you have to look at them for failures. And when I look at what you've got right here, it concerns me a little bit because you've removed a lot of the bulk plate material right around the area where the stresses are going to be.
Okay. Yeah, yeah, we'll have to look at that. We can do. I think the Y would probably be the best for us.
Yeah, that's fairly common. Now you may not be able to get, you know, Y connectors for it,
Right.
but that is commonly something that's done when you get up to the size and the weight that you got as you know, as you go with that Y connector. And then that lets you put, something like a fender washer around the all thread. Because that's structural too with the design.
Okay, yeah, we could put like now I see what you're saying. I was thinking like an aluminum plate on the back end of this too, but that would be a similar issue. Okay, and then real quick, I'm gonna go ahead and my phone, I had it running since the beginning of this meeting, so I'm gonna switch this over to Leo's phone, just so it doesn't die on you. So just a sec. There we go. All right. So you
The
so now we're on a winner.
Okay, I have to try to get that screen to be big now. Okay, I think I did it,
Great.
but the audio is not quite so good.
How's this? A little better?
Yeah, it's a little faint is all.
Let's see if we can fix that.
That's good right there.
Oh, that's good.
Yeah.
Okay, great. All right, so yeah, we can we'll look at this because that's a really good point, especially with us increasing the diameter on this. Our walls between them are getting kind of thin.
Yeah, kind of look through the whole rocket at that particular part of the structure. And see if you can make that a little bit more robust.
Sure. Yeah, it's something we'll see kind of down the road here. It might be a little difficult with the avionics space, but that is thing we can improve on. Yeah, same thing here. Okay, so we'll look at that. With the avionics bays, same on both sides. We have the screw terminals, like I mentioned before, and there are two charge wells for main and secondary, or primary and secondary, and then they're all marked with what section they belong to. So then our chute protector, like I mentioned, is connected here at the bottom of the coupler against the charges. Like I mentioned, this is a hard point, so this is not the shear. We have our chute protector chute, the Kevlar shot cord comes in, secures at the bottom of the protector, and then our chute, which I have down here, packs into it burrito style, protected from the black powder charges. So then come down here, you can see we have the shot cord is bunched up. Usually we use masking tape for that, just enough to restrict movement, not extra wrapping or anything, and it breaks apart very easily. So then this is where we have our first payload. This is the quadruped, Sara. Our main chute packs in first into the chute protector, or the chute bag. Then the payload packs in front of that with the payload chute tethered to the shot cord with the chute protector, but then the chute itself is separate. The payload chute comes forward of all three. So this is the connection inside the rocket. And when our coupler comes off, like this, it pulls the main chute out of its protector, pushes the payload out, and then the payload chute deploys before the main does.
Okay, so yeah, the payload is sort of free to move back and forth, isn't it?
It is. That's why we try to pack them pretty tight. The one thing, so one thing that restricts the movement of the payload is the shot cord pack behind it, and then the chute pack in front of it, and that's connected to the shot cord here. So it's still somewhat restricted, but it is allowed to shimmy back and forth, just as it compresses the shot cord and the main.
Okay, and you said you were using 4 number 6 shear pins?
4 632s. Yeah.
Yeah, I don't see a way to improve it right at the moment. That is a concern, though. It's worth kind of thinking through, because I'm not sure, who actually will do the safety review on site.
Right. Right.
Um, it might be me, it might be somebody else.
So we do fortunately have precedent for the past 4 years deploying payloads like this, but it is something we've talked about. If we ever end up going to a larger body tube, um, creating a more robust deployment structure, because right now as it stands with the 4U form factor, they can't slide this way. They just kind of slide in and out. But it is one thing that the team has their eyes on right now.
Okay, so what happens if because the payload can move?
Mm-hmm.
Let's say hypothetically that you had some horizontal velocity, and so basically you put out the main at the top. So
Yes.
what's going to happen to that payload at that time?
Yep. So what happens is the payload will deploy if the main deploys, because it's the main acts kind of like a piston head to push the payload out. If the main deploys and the payload deploys, you just have a really long recovery. So the payload has its own tracking system, but we're deploying main for both at 11,000 feet. This is descending at about 28 feet per second. The payload is coming out at I'm sorry, this one is 29. Payload is 28. So they'll recover near each other, but it will be a long recovery.
And you have GPS on both payloads?
Yep. Both payloads have GPS.
Yeah, as when you get ready for your safety review on site, I mean, put your thoughts together on how you feel that this is an adequate design, and how it's not going to put out it's not going to cause the main to come out at apogee,
Sure.
whatever testing and logic that you can come up with. And if you can come up with additional ways to minimize its movement, it would be good to be able to say that.
Okay. Yeah, you can't see. I'm nodding right now. I got you. We have some shock testing in mind, and we can do that, and then we can look at like how we pack the shock cord and see if we can try to restrict movement even more with that. Maybe even put some dog barf in or something. Okay.
Yeah, I mean, I was kind of wondering, like, if you could put an extra blanket or two in there so that it would act as a damping up on top, because it's up on top where it's going to act like a battering ram against your.
Right. The payload chute helps a bit with that, but yeah, that is an issue.
So what is the payload chute, or what are the chutes? Let me just ask that. I see the
Yeah, so booster chute is so we have a 3-foot drogue, 10-foot nylon ripstop nylon booster, 42-inch nylon for the payloads, the 42-inch nylon also for Sauron, which I'll show you in a second, and then a 9-foot main for the sustainer.
And whose chutes are they? Or are they toroidal or elliptical, or what?
Oh, these are all elliptical.
Okay.
Yep. And they're fruity shoots.
But not the toroidal ones.
Correct. I think, yes, they're all elliptical. Let
Okay,
You've got me second guessing. Let me confirm that. I'm 95% sure they're all elliptical. All right.
now, I think I see some knots there along the shot cord. Is that the case?
Oh, we have, so like I mentioned, if we wanted to, we could put our swivel link connection like this. That was just an option. We usually do the quick link, swivel link, quick link. And then here we just have the shot cord moves through our shoe protector here to keep it in place. No other knots on the cord.
Okay. All right.
All right. Oh, actually, sorry, one more. This is from same configuration, but we're gonna take this out. And then we have the shot cord connects to our interstage coupler here, which then connects inside the fin can for the sustainer. So the one thing, the interstage, we have shear pins on this side, the same 4/632s, and then this side is just a friction fit with the interstage. So no shear pins or anything for stage separation.
Okay, so those are surface mounted fins for the sustainer.
Yeah, so they're surface mounted up to 7 inches in. I'm sorry, 8 or 9 inches in, 9 inches in. And then the remaining, we have a fin tab up here that's about 8 inches long, and that goes in between centering rings. So it's a hybrid mount.
Okay. Do you have the shear pin or the rail buttons mounted on the booster yet?
They are not mounted yet, no.
Okay, I saw the position of them in the open rocket, and you had 2 on the booster and 2 on the sustainer. Is that still the plan?
We have 2 on the booster. I think we might bring the sustainer down to 1. The reason we had 2 before was so we could do a sustainer test flight, but we would be interfering with the interstage coupler if we kept the 2 on for the full scale.
Okay.
Yep. The reason we have 1 is just so we can keep things lined up on the pad.
All right.
Okay.
Well, before we leave the bottom of the sustainer, how are you doing the thrust transfer on that?
Yes, so this is standard practice. So we have our sustainer motor. This is not the fully loaded motor, just to keep 1 sec. So motor tube is welded to the centering rings with epoxy, and then we have again centering ring here, centering ring here. So we have epoxy in the joint between the tube and the rings, and then the rings are epoxied to the airframe, and then we have the fin tabs which come through the airframe between the centering rings. So thrust is transferred through our motor tube here to the centering rings, and then through those centering rings to the fin tabs to the airframe.
Okay.
Yep. So it's a lot like the Ultimate Wildman kit, except he has the centering rings from the bottom to the top. We just have them up here.
Right, but I think it is good that the centering ring hits the fin tab.
Yes, yes, yes.
Tell me a little bit about how you prepared the motor to glue.
Okay, so this might be a better question for our aero captain, but I know the general. So Pete, if you want to, but for general preparation, they sand all of the surfaces that they're epoxying, rough them up, and then apply the it's Proline epoxy in this case in one go. They don't do layering. Fill it with popsicle sticks, get to about a 1-inch fillet, and then let it cure before slipping them and doing the other things. But I'll hand the mic over to Pete here because he can give you a better overview of that.
I can actually.
Yeah, he'll go in on his phone actually.
Jim? Hello?
Yes.
Thanks. So what questions would you have? I think Phoenix covered the general pretty well.
Well, the one step that I didn't hear, which is something that I would always do when I'm gluing something together.
Sand the surfaces first. I don't know if you said that.
Well, I would sand them, but it kind of depends on what you're gluing together. But the concept is that you, instead of just pouring in the epoxy to make your fillet, you actually rub the epoxy into the surface that you're bonding. So I call it buttering the pieces.
But I think we do that. We kind of set the fin in, and then you see like switch my camera, or it's showing. We kind of rest it like this so that there's a nice fillet shape being made by like gravity, and then we kind of take a popsicle stick and rub the epoxy along the fin portion and the fin can portion with tape kind of lined up, or I guess you can't see, like tape lined up right here, and we kind of rub it with a popsicle stick on all the surfaces.
The camera.
Yeah. So we kind of put tape along these surfaces, not leaving open this, and then we would rub the epoxy with a popsicle stick inside this surface on the fin can and on the fin itself, and then we kind of let it sit once it's hardened to make that nice fillet shape with gravity. I don't know
Okay.
which phones.
Yeah, it sounds okay, but just make a note to file. When you glue surfaces together, you want to physically get in there with a glove tip or finger or whatever, and just literally wipe the epoxy on the joint that you're going to be gluing. And then when you put in the fillet, that gets the epoxy down into the sanding scratches and that sort of thing. So you're not just spreading the epoxy out on the surface. You've already worked it into the surface that you're bonding.
Yes.
That sounds like something different than what has been done here. It's not the popsicle sticks just for smoothing. It's not rubbing any epoxy in.
Right. Yeah. A good practice on the epoxy joints is to, basically try to rub the epoxy into both of the surfaces that you're gluing together. And it'll vary. Are you putting in a coupler? Are you putting a fin? I mean, it depends what you're gluing. But that's the secret to getting a good bond with epoxy, is doing that buttering of the pieces. I've had teams just recently that put in a bulkhead on a coupler, and they probably had fillets that were, I'll bet you there was a half a pound of epoxy on either side of that, and bigger fillets than you've got on the fins. They're almost like like they were made with a 2-inch diameter pipe, and they had a hard landing, and that bulkhead just popped right out. And the reason that it did that is because they didn't butter the surface of the tube that they were gluing the bulkhead into. So the epoxy just let go. Okay.
All right. That's good to know.
Yeah, that's the essential step. It really is important to do. So maybe add it to the repertoire for as you continue to glue stuff together, that, got to sand it, clean it with alcohol, butter it with the epoxy that you're using, and then you can go ahead and, add the bulk of the epoxy and smooth it out.
And is it best to make sure that when you butter it, you put the full epoxy before the buttering cures? So you can like butter it and then fill it?
Well, all at the same time, yes.
Okay, okay.
Depending on what it is that you're gluing in. But, it's working the epoxy into the surface that you want to bond that is what gives you the grab. Otherwise it can just pop right out on you. And I think that the team that happened to was very surprised, and they put so much epoxy on there. How could it possibly let go? And the reason is because it wasn't prepared properly.
Gotcha. Okay. That is good to know. We'll keep that in mind moving forward. Okay, so rest of the fin can, is there any questions you have here? Standard, and these are all hard points on this side.
Okay.
Okay. So then we go to our first coupler. This is the interstage coupler. Hard connection on the fin can side, shear pin on the far side. We don't have it yet, but on this plate we have our holes down here, which we feed the wires through for our interstage separation and then air start. And then those actually, you can kind of see we have holes in or a hole in the retaining ring up at the top left, and that's what we feed the wires through on the aft end.
Okay.
Okay. All right, so then forward into this, like I said, shear pins. It's the same drogue harness setup as before. We'll look at the holes on these, see if we can do the Y on the shock cord, make that stiffer. 40-foot 3-loop shock cord, 1/2 inch, comes in through our payload or drogue bay, and then it comes to our altimeter bay. And we have this one opened up so you can kind of see how everything's lined up. All of our altimeters on one side with the featherweight or the Easy Mini, the featherweight tracker right there, and then on the back side we have all of our batteries zip tied. This one also has a cross zip tie. It's just not right now.
Yeah, I can't see if you're doing this with your batteries. The zip ties are good. One thing that I typically do on the 9-volt batteries is I'll take electrical tape and I'll just wrap it around the battery to hold the connector to the terminals.
Okay. Yeah. So for our cross, yeah, that's a good idea actually, because our cross, it goes under the zip tie goes under the terminal, so we can do that. Make sure those are tight. Yep. And then we have Velcro on the back side to keep the battery from moving too much as well. But yes, we can do that. And then, like I mentioned, everything is wired through screw switches. These are the 3. It's the reason we have this shape for our holes, to make sure that this part of the sled can slide through the coupler without interfering with the hard point screws.
Okay.
Yep. So otherwise, aside from this being open, the interstage coupler is set up the same way, or the sustainer coupler is set up the same way. We have chute protector, the chute bag, hard point, Kevlar shock cord is inside the protector for the bag, and then our main right here comes through, and this is a 9-foot main. And then our payload, this one is a 4U CubeSat Sauron, and as before, it packs main, then payload, then main chute. In this case, we have a large chute protector, and then the nose cone on the top.
Okay.
Okay.
Do you have anything else you want to show me?
Nope, that's about it. If there's anything else you want to look at?
Well, let me go to my list here.
Or
Okay, I think we've covered everything that I have on my list. You know, the thing that most concerns me is the lids on the altimeter bays and so forth, just because
okay,
they're not backed up. You don't have metal backing on them. You can't use fender washers,
right.
but they're the structural elements. One thing that, I mean, the way that I would probably do the bays is instead of having a U-bolt, I'd probably just have all thread go through there and eye nuts, such that, you know, and the concept is something that I call a single spine. You're going from harness to all thread, from harness to all thread, and the bulk plates themselves then become non-structural.
Okay, so you would take like an eye bolt with a nut on the end instead, thread that on, and then put.
Yeah,
Yeah.
so you'd have an eye bolt or eye nut on either end
Mhm.
of a piece of all thread.
Right.
And then you've got to do a little something to prevent that eye nut from unscrewing, which is easy to do with some safety wire and so forth.
Mhm.
And that way you take the bulkheads out of the
Out of the
equation.
equation.
Now, you know, 6-inch, well, I mean, that's how I would do it on 6-inch. Sometimes, you know, as the rocket gets larger, you kind of wonder about having a single attachment point. I'm not sure I do it that way for 8-inch. I'd probably go more with the Y connector on 8-inch. But
Okay.
6-inch, I'd probably just use, you know, like a single piece, probably 7/16 all thread through there and eye bolts, and then I would have and just take the bulk plates out of the equation. Just exactly for the reasons that I don't like the bulk plates that are there now.
Okay.
That structure is kind of compromised, and you really can't adequately reinforce it there with the U-bolt coming up and the all thread going down. You don't have the ability to reinforce that section. So
Okay.
that's the main thing that I'm concerned about. You know, the other issue is just the payload moving.
Right.
So maybe give that a little bit more thought. And you wanna go look for that altimeter programming email, so that if you can't find it, let me know and I'll resend it to you.
Okay. Yeah. Yeah. We'll look for the email. We will make sure that I get you the numbers for the the sizing of the chutes, and then there was another thing I have with the notes on it that I'll send over. Oh yeah, the OR numbers for descent rate if our sustainer doesn't deploy or ignite. Okay, and then we will look at redesigning these coupler hard points.
Okay. Ben, you've been kind of quiet. You got any comments from what you've seen? You're probably muted if you're talking. I can't quite tell.
Yeah, he's muted.
Well, I thought I pushed the space button, and never mind. No, I thought Jim was an excellent review to start out with. You caught a couple of places that we hadn't seen yet, which was the bulk plates. I've done eye nuts before, and they work out good, exactly as you described. So I think that's a good way to go from there. In terms of the SRAD motors, I think we're clear there. They will do their sustainer static fire tomorrow. So, and that will get plugged in. So I think we're all in good shape from there. So,
And one thing I want to mention before we head off, is I think I forgot to. So you see, for the external, the thermistor electronics, we actually have. Let me show you a second. So we're epoxying wires like this along the length of the rocket to feed to our thermistors. Just make sure you're aware of that. So we're gonna have a line of epoxy like this.
And that'll be for the spaceport flight. Did you have that?
Yep, that'll be for the spaceport flight.
Okay. Yeah, I think it's okay.
Okay.
It'll just add a little drag, but,
Hey, actually, they need a little drag.
Yeah, we do.
uh-huh.
So,
And, you know, go ahead and develop that program for for lighting the sustainer. And kind of follow the directions there, because you have to be, you know, kind of precise about the timing on your, you know, on the separation charge, and then when you're going to light the motor, and then when it's
Yeah.
pressure. You know, I've had teams say, and you sort of have this. Well, let me say, for example, you said you're going to separate at 1 second and then light at 2 seconds.
Right.
So sometimes when people tell that to me, I look at their simulation and they actually show the motor coming up to pressure at 2 seconds. So it's one thing to light the motor, and then you have to have another delay before it comes up to pressure. Maybe a second or something like that. So
yeah.
Okay.
it's a matter of being a little bit rigorous on how you set up that timing of that. But what I want to see is the actual timing. You know, when are things going to happen? When do you think it's going to come up to pressure? And have that linked to the altitude check.
Yeah.
Sure.
I was just going to add that when we do the static fire tomorrow, it will be the same configuration as the sustainer. So we'll have the cover over, and we'll get a real good feel for how long it takes to come up to pressure.
Yeah, and it'll take longer when you're in the air.
Yeah,
Than
understand.
on the ground. It'll probably, you know, you want to add a half a second or a second to that time. And it just matters, you know, when you're trying to predict your altitude. But you know, you just want to know that that's going to take a little more time.
Okay.
Okay. Yes.
Anything
Yeah,
else?
we'll look at that. That's all for me.
Questions or comments?
No, I think we're pretty comfortable. I'll make sure I'll send you the new configuration for the altimeter. Make sure I get the update that you sent out.
Okay.
I think we're good here, at least with the rocket assembly. Thank you for pointing out the U-bolts. That is something we did not notice, so it's good to be checking on that.
Okay. Okay, if you have any questions between now and Spaceport, just holler at me.
Sure.
So we'll see you there.
Okay, we appreciate it.
Okay, you bet.
Hey, Jim,
Yeah,
be sure I'm copied on that, on the Raven settings, because
Me too.
or your altimeter settings, because I didn't see the email either, so.
okay, I may not have sent it to the FORs. I'll have to go back and check, but I'll just go ahead and send it to you guys anyway.
Great,
I would appreciate it.
greatly appreciated.
Okay,
I'm building my own two-stage,
there you go.
so I want to see how you do it.
Well, I get kind of prescriptive on the timing for it, just because, you know, we don't want them doing funny things. We want to,
No,
you know, I see a lot of people, for example, they'll say, well, I've got to, you know, it's conceivable that it could light anywhere from 3 seconds to 12 seconds. And it's like, no.
oh, no,
You
that
want
doesn't sound good.
to control the time interval that the sustainer can light during, you know, and control the flight. And it's not difficult to do it. It's fortunately with the Blue Raven and with the Telemega altimeters, it's easy to do. It used to be difficult with the Ravens. The Blue Ravens are easy. The old Ravens were not. So I'm glad to see, you know, if you're using the Blue Ravens, it makes the programming for the sustainer a little bit easier.
Yeah, I want to get one. I don't have a Blue Raven. I have some of the older ones.
Yeah, the
And
old
I
Ravens
hate
are
the
fun.
magnetic switches with a
Yeah, the old
passion.
Ravens are funny. You have to they trigger on altitude, not time, and it's difficult sometimes to get a good program with them.